Well, welcome everybody to this exciting launch of the next book in the Perfect Reliability book series. This year, have decided to take a lot of the most common reliability tools and release them in some nice small little handbooks that you can easily share with somebody who wants to know a little bit about the methodology, or hopefully if somebody wants to learn about it, they can take it with them on an airplane and read them. It's less burdensome than taking a big thick book. So that's my motivation for these. And in creating them, first, Devastate the Competition recently came out, which is another one of my third larger book. And this one focuses on how to take market share through robust design. So keeping the business objectives for your product development program, connected to the actual process, so you end up actually releasing the product you intended to make. So my vision for these books, these nice small little handbooks, some of it came from a book that I have always loved, which was a Volkswagen maintenance book that was written decades ago. And if we say, Arn, I don't know if you could just mute everybody else right now. It would be good. I just always loved I loved how much it used illustrations to communicate ideas. So I tried very much to do the same thing with this book series, to include a lot of illustrations, kind of keep you engaged and share the concepts in a very dialogue, kind of manner. So that's the spirit of these. So let's go right into it. Let's talk about auxiliary life testing. That's what this one is about. So auxiliary life testing, the idea is we're able to get to observe what will occur in the future in as short a time frame as possible. So that's why the idea of a time machine, is really the spirit of it. Can we see the future in a much more compressed time frame? And you can, if you are able to isolate. You'll see a few key components of what's going on, and continue to use the guidelines for auxiliary life testing. You should be able to accurately predict what can happen in a much longer time frame in a shorter test. So let's start off with language, which is always, one of my cornerstones. And let's take a look at one of the formal definitions of reliability. It's the probability an item will perform its intended function under stated conditions over its useful life. So there's two key parts here: the probability that will perform its intended function and useful life. These are the two elements that will help us really define the key characteristics of our product with regard to reliability. So let's take a look at these. Let's break them down a little bit here. If we have our product, the probability of performance intended function is looking to address, assess, measure, set goals for when will the product break. And these are not failure modes that are guaranteed to happen for all products. These are random things that can occur during useful life and are unexpected. So what about the second one? So useful life is about when will it wear out. And these are predictable. And these failure modes, to some degree, for any product that lasts long enough, they will experience them because it has to do with actual degradation from the expected stresses. So it's really important to differentiate between these two types of failures. And especially when we're doing something that is as specific as auxiliary life testing, you have to make sure that you're always keeping these two separate. So let's take this to the bathtub curve. For those of you who aren't familiar with the bathtub curve, it's a graphic used in reliability to share some of the fundamental phases of product performance through life. And the idea here is, if you have time on the bottom axis and failure rate on the vertical axis, a new product, if you were to release 1,000 new products all at once, manufacture them, there would be a failure rate that would happen to be higher, that would slowly fall out, which would be driven by manufacturing defects. Of course, this curve is very exaggerated, but those will occur, and then they will pretty quickly dissipate out. Then we will hit the main useful life part of the product's bathtub curve, and this is where random failures occur during life. So if you look at that population of 1,000 units, you would see a lot of different types of failure modes happening at intervals that aren't necessarily predictable. And this is when we talk about reliability, really what we're talking about, the reliability, the random failure rate during use life. And then as we get to the end of it, we will begin to see wear out failure modes begin to become dominant. And this is where the failure rate will just continue to increase until all units have failed from wear out failure modes. So if we take this definition and we look at where this is represented in the bathtub curve, that failure rate, how high is that failure rate on the axis is the probability part. What's the probability? The higher the probability, the more likely you are to have those random failures. The second part, useful life. That is all about when does this begin to become a dominant behavior? When does useful life end? And what we're looking to do with accelerated life testing is we're looking to measure that. That's what this is all about. This isn't about right now controlling it or modifying the design. The accelerated life test is designed for one specific reason. Can we measure that time to when the wear out failure modes begin to become dominant in the population? So since it happens for all of them, I don't even like to call it a failure, really. I mean, wear out failures are really a design characteristic when you get down to it, right? It's a 60,000 mile tire that wears out starts to wear out after 60,000 miles. It didn't fail. That's how the end of a good life, a good product's life ends. So it's part of the entire characterization of the product to make it successful in the field. You want to select, you don't want to have something that has infinitely long life because it might be way too expensive to manufacture or require, inventing technology that'll take years to do. And it may not be what's appropriate for the product to be successful. So this is another design characteristic that is selected early on. And we use accelerated life testing to measure how it's performing, which then may have us do things to change the design to have it satisfy life if it's not, or maybe even we use that measurement to know we can do cost reduction because we have, far too long a life, or there might be another parameter that we want to optimize. And in doing so, we would want to be able to measure life because we want to make it shorter. So there's, I like to, over the bathtub curve, show this, this gradient on top of going from improve reliability to measure reliability. And the reason why I like to do that is I think that the reliability tools tend to all have their very unique balance of these two objectives. So you might have things like halt testing, where the objective is entirely to improve reliability. It really doesn't offer a lot in measure. It gives up the opportunity to measure behavior by so that it can very quickly provide input to help engineers improve the design. And you have at the other end, you have accelerated life testing. Accelerated life testing is really entirely about measuring a parameter, the wear out parameter. And in doing so, it's extremely surgical with regard to how the test is designed. And it also gives up the opportunity to provide a lot of insight into the design. So for example, if you find things that are abnormalities and you weren't expecting in your tests, you're not going to use accelerated life tests to try to understand them further. You're going to pull other tools out of the toolkit to do that. It could be halt test, it could be stress margin testing, it might be reliability growth. But accelerated life testing is really looking to do one simple thing. It's looking to measure the behavior of the wear out failure modes. So I just want to take a moment and have Arn, if you could unmute everybody. I would love to answer some questions right now if people have any questions up to this point.
Adam, this Subramaniam from India here.
Hi.
Hi. So when you say that time to wear out, do you define it as end of useful life?
Yeah, so that's a great question. So of course, there can be different types of wear out failure modes that can occur, right? So for that tire example I gave, obviously one is the tire tread wearing down. Another could be dry rot, right? Where the tire just from UV exposure and ozone begins to break down and crack. So that would be those two would experience those different wear out failure modes from different use cases, right? In one where it is the dry rot, it might be in super high altitude where ozone is higher, and it might be a tire that doesn't get used as often, right? That's why they put years and miles in the warranty. Whereas the one that wears down first would be one that did a lot of mileage. So you would have to set that goal, as I said, as you're setting the design parameters, and then look at all the different types of wear out failure modes that can occur, the stresses that are related to it, and see if it can satisfy that, design objective characterization, and then make modifications. So you get to decide when the end of useful life is, and then modify the design to satisfy it, is generally how the process goes.
Yeah, thank you.
Good question. We'll take one more and then I'll go back into it. So an example of not wear out is a ship hitting a bridge. It didn't wear out. That was a random. If you're going to categorize it, that was, random during use, use life failure. All right, there's no more questions right now. I will continue. I know it's a little bit harder online to have to jump in and do questions, but let's move on. So next thing I want to talk about is the type of failures. Like I said, it's very surgical in the sense of you are in advance very carefully diagnosing and characterizing what the wear out failure modes are. So if we're talking about compressing this in time, or where we're going to take elevated stresses to compress it, we need to understand what we're working with. And I like to, a lot of times we use the term physics of failure kind of generically for understanding the mechanisms that make something fail. But in this case, I like to use two terms, physics of failure and chemistry of failure, because it is very important to distinguish which you're dealing with before you begin to construct your model. So let's take a look at what the difference is. So physics of failure is something where you have accumulated stress that causes, actual fatigue, right? And so one example would be if you apply temperature to, if you had a copper material and let's say a steel material attached to each other, and you applied heat to it, the copper is a greater thermal expansion coefficient and will bend, this bimetal part in one direction. And then if the heat's removed and it's cooled, it will return, right? And if you continue to cool it, it could even go in the other direction. So even though this is temperature, this is causing mechanical fatigue. And for that, a very common model is the Coffin-Manson model, which uses these temperature cycling in an elevated way, more extreme range, that can compress the time it would take for that fatigue to cause the failure in a normal use case. So you could take, for example, 10 years of, let's say, cycling fatigue for a product that is outside and goes from daytime to nighttime. So every 24 hours, we'll do a full cycle and do 10 years and be able to compress that to a few months by doing a greater temperature range and use the Coffin-Manson model to then to extrapolate it out to the full life. So another is the chemistry of failure. So an example of this would be something like an electrical capacitor, where it has heat applied to it, and over time, what occurs is enough material property change that it no longer performs correctly and fails. So what's happening here is the wear out mechanism is material properties change from exposure to oxygen over time. Now, that's a chemical, chemistry reaction, and chemical reactions typically can be accelerated by applying, elevated temperature. The more temperature is, the faster the reaction occurs. So with the Arrhenius model, what we're able to do is we are able to apply a higher temperature, have the failure occur in a shorter time frame, and then use the Arrhenius model to extrapolate that out to what the true time to failure would be in the use case. So let's just dive into that for a little bit so we can understand it. So I always love this example of cooking onions, caramelizing onions, where I want to talk about, because effectively cooking is doing chemistry, right? You are using heat and increasing it to increase reactions, typically with oxygen and other elements, to modify the food molecules. So onions are interesting in that a new onion, let's see if I can put this out of the way. You know, an onion that's at room temperature on the counter, if you leave it for 5 months, it will spoil eventually, right? Left at the same temperature over time. And there's that rate of reaction for the room temperature and whatever chemical reactions are occurring with the environment, that will progress at that rate. But this is exactly why we have refrigerators, right? Because if we reduce the temperature, we slow down that reaction. And that's why we put things in refrigerators that we're going to use in the short term and then put them in the freezer for the long term, because we are taking the heat away that drives that reaction and it's slowed down. So the onion put in the fridge for 5 months might be the equivalent of an onion on the counter for a week or 2 weeks. And so, we are, I'm sharing this concept with you maybe for the first time, but you're actually very familiar with it. And then if we want to further accelerate certain reactions, we will heat them up, and we will, do that to create an accelerated version of it. So when we do the cooking with the onions, what we're looking to do is we are looking to extract sugars from it. It creates sugars, it makes it sweeter. So within 15 minutes, you can create X amount of sugars and change the taste to be sweet. So this would then be, with the Arrhenius model, we should be able to take this and extract it out to how many sugars there would be on for one left on the counter. And we should also be able to, with the Arrhenius model, show that at a lower temperature, that in 10 months you would have the same amount of sugars extracted. So we are able to take the same reaction of the onion molecules interacting with oxygen and change the temperature, which changes the rate of reaction. But the Arrhenius model would allow us to correlate all three together. And so that's really it. So just think about cooking food, putting food in a refrigerator or in a freezer, and what you're doing is you are, either compressing time or extracting it out for those same reactions to occur. So you can study what would happen in a longer term in a compressed time frame. But this example I also love because it is a great opportunity to begin to talk about pitfalls. Because as I showed earlier, if you leave onions on the counter for 5 months, they are not sweet and delicious like caramelized onions. They are rancid and spoiled. So what happened? Why does the model fall apart? So this is where we're going to talk a little bit about some of the common pitfalls in accelerated life testing. And this one is great because what I've done here, and this is where I was talking about accelerated life testing being very surgical. And by surgical, I mean it's precise, very well thought out. You might have done some experiments earlier to understand it. The mistake we made here is that it's not the oxygen just interacting with the onion that's changing it over time. There's bacteria that is interacting with it that's making it rancid, right? It's that rancid poison that makes the onion horrible when it's been left out too long. The sugars are occurring, but at the same time, toxins are being made. So when we put it in the pan, there was 2 mistakes. The first is the elevated heat did not accelerate the bacteria in the same way. It's not going to go rancid quicker in the pan. But also, it definitely isn't, because the heat actually kills the bacteria. So even if slightly elevated temperature would make the bacteria go higher, we were at such a temperature that we would have killed it. So we actually eliminated what was the true wear out failure mode, which was, going to be the wear out being we no longer want to use the onion for food, being the bacteria driving it. And we also were using the wrong accelerator. So it's a really good example of how, if you're not careful and take time to truly understand all the interactions that are happening over time, you can very easily make a very bad prediction based on your accelerated life test model, because we would have advised people to eat these delicious sweet onions by just leaving them on the counter for 5 months. And that's not the case. But it's also interesting because there are other foods that we do let age in ways where we then do enjoy the taste, but we usually do that in cold environments, right? To where it does inhibit the bacteria apart from the cold, but the other mechanisms can still occur. So again, that's why I keep using the word surgical. You really have to take time in advance of accelerated life testing to ensure that you are studying and using the right principles for the models you're using and the stresses you're applying. Another common pitfall is taking a design that you have that you've done accelerated life testing with and you've validated it in the field and just applying it to the next generation product. So let's say that the primary wear out failure mode for this motorcycle is the harness becoming the plastic connectors getting brittle and failing and disconnecting. So if that's what we know historically, and we know that the brittleness generally is in direct relation to the heat from the engine, and we had a model for that running at an elevated temperature, and we've validated that that totally applies to our bikes historically. So here we are with this new bike here, and we're just going to put the same harness and assume it wears out the same way. But one big mistake, the previous bike had body fairings on it, body panels. This one does not. So the bike is very similar. The harness is used in the same way in the same motor, but those panels are no longer there, which means now we have sun exposure. So now these connectors that did not see sun exposure in the previous models do now. And it turns out that the UV actually breaks down the plastic quicker than just the heat alone, which means now this harness is going to wear out much faster, even though it's the exact same part used in a very similar application on a very similar product. All it took was that one change of removing the body panels, and our previous model is no longer valid. We would need a new model and a new test that uses both the UV and the heat. So that is another very common mistake. Another is we will take something and run it in its normal manner, but do it much harder. So for example, if you were to take a motorcycle and race it, and then say, well, 1,000 miles, of racing time, or 1 mile of racing time equals 1,000 miles in the street. It's just kind of a generic statement across the entire bike. That's not going to necessarily be true for all the components. You might have done a study to find out that for the pistons, that is actually true, that 1 mile of stress on the track equals 1,000 miles in normal use. But is that the same for the electrical system? Is the electrical system really being stressed in any way greater than the normal use case in the race? It's not. So we have to be careful with these blanket statements, and they can be very convincing because you have actual specific, features in the product that does have that correlation, to then just say, well, that's the same correlation for all wear out failure modes. So that's also a very common mistake. So even if something has a very convincing explanation, it has a lot of data behind it, and you've shown that that's how the engine components correlate to real use, we can't just take it and just throw it to the rest of the system. So that we have to be very careful of that as well. The next one, very common pitfall, is using the correct data sets in observation. So lots of different kinds of failures can occur in a test, but we can't just take them all and use them in our statistics and our math that we're doing to make statements. If you were to crash a motorcycle and have certain failures occur, would you just take those failures and put them into your calculations for the accelerated life tests? You can't, right? Because those are stresses that are different than the relationship you had for the accelerated life test, where you had a primary stress to wear out failure mode relationship you were looking to study. It doesn't mean these failures can't occur, but something like a crash is more along the lines of the types of stresses that would occur, randomly during life. What kind of impacts? It doesn't have to be a full crash. What type of conditions that are not expected to be consistent would occur. And you might see some of these when certain things happen in accelerated life tests. So you have to be very careful to take them out of the data set. Which brings us back to our bathtub curve and the different types of failures that make up the curve, different phases, and bucketing what we found. So what I mean by bucketing is you have failures that you will root cause to be manufacturing defects. So those should be bucketed for the infant mortality part of the curve. These are obviously not going to be used in the accelerated life test study. You will have failures that you will be able to root cause back to the normal use case stresses and accumulated stresses, but also all the random variables that can occur there. So those would be in the bucket of use life. We want to be careful to only include the ones that are in the wear out part of it. So in doing so, we will have, in doing so, we will make sure that we are only in this case taking the failures that are in the blue bucket and using it in our math. And we can validate that we are doing having the right ones, because it should have a behavior that when we study statistically matches what a wear out behavior would be like. A wear out behavior should be quite predictable. So to some degree, the probability density function should be a bell curve, right? And if we were to do a Weibull analysis, that would be a beta shape factor of 3. So if we saw behaviors for the data set we had that were very different than that, we should examine it again to see if, one, maybe we've contaminated by including behaviors from some of the other buckets accidentally in there, or maybe we've made a mistake with regard to what stresses we have in our test and having them correlate to the wear out failure mode that we wanted to study. So another pitfall to be aware of is, are we validating our model? Like many things, the success in an initiative is in preparation. And accelerated life testing definitely has a very strong emphasis on that. I mean, we do lots of things in our life. I like the example of, if you're painting a wall, in your house, if you just go and paint it, it's probably not going to look too great. The way the paint looks great doesn't have anything to do with how you put the paint down. It has to do with all the preparation. Are you going through the wall looking for where there's bumps? Are there cracks to fix? Are there parts that need to be, taken out and replaced? It's going to be all about the preparation with regard to if the final product looks good. It's not how you actually, it's not going to be only how you take the brush and put the paint down. Same thing here. When you have decided that you have identified your primary stress to wear out failure mode relationship, and you've created a model, you want to validate it before you go forward within, your big investment in this test. And the way to validate it is to run it at 3 different levels of stress and to look to see if they, when you take the results and you compare them in compression, do they match to show the same variables? And we'll talk a little bit, in a moment about some of those variables. But you have your model, which has specific factors in it that you've selected. That, in the case of the something in the Arrhenius model where you're using elevated temperature, what are the factors within that chemistry reaction, and are they showing to be consistent at those 3 different levels? So not validating your model is another, big common pitfall. And it's really hard to do because you are in a product development program that has a lot of time pressure. And that time pressure, makes it hard to make the case of, hey, can we do this whole phase of just validating the model? So I highly advise with this to try to find ways to, outside of a product development program, to validate your accelerated life test models. Simply doing them, in the program, even if you are able to do them there, they're going to become pretty compressed. And a lot of your technology is going to carry over through, obviously, several of your products. So doing it outside of a specific product development program and having a very well-validated model can be quite tremendous, because you can then use it with great confidence, and you'll probably be able to figure out how to make the exercise shorter in all these product development programs. So it is very high returns if you do that. Now, even with a validated model, you have to be careful that as you try to compress and run the test faster and faster, you're going to be getting up to limits where other things can happen. And, so we have a model that we validated under, a specific, stress that's above normal use case, but then we want to take it and compress it farther by running it at 5 or 10 degrees or 15 degrees C higher. Well, here's the thing. Every little bit of error you have, even, small tolerances, is getting magnified as well. And so you can very easily take what was a very small margin of error, it didn't matter, and magnify it to a degree that makes your predictions extremely far off with the same validated model. There's also the risk as you get closer to the limits of the product's performance that you cause other kinds of failure modes. I mean, just simply, right, picture taking temperature up higher for a material breakdown. Well, you actually can end up melting things or burning things or causing failure modes that would not be a part of a normal degradation over time. So we have to be really careful about that as well. So how does maintenance fit into all of this, right? Because we do maintenance because things do have predictable degradations. So let's just talk a little bit about that. So if we did a study for our product, for in this case, the motorcycle, and we noticed that the brake pads were the first thing to wear out, and we didn't, we found it was not going to be easy to design brake pads that would work sufficiently and last our full, let's say, 10-year life we want for the bike. Do we say that, that's it, motorcycles can't last longer than brake pad life? Well, of course not. So we have a couple options. And one is to do preventive maintenance, which means we change out the brake pads and start the curve over for the brake pads. And effectively, then the brake pads are never part of the wear out of the motorcycle. No motorcycle's ever been considered, time to throw it in a junkyard because the brake pads were worn down. They're now went from being the thing that shortened the life most greatly to something that's not relevant. Now you'll notice here, I didn't just draw it continuously as a flat line. I show a sawtooth here. And the reason is it's good to also remember when you're designing preventive maintenance programs that you are starting back at the beginning of the bathtub curve, which means there's an opportunity for introducing new quality defects. And this does happen. I'm sure you've had experience where maintenance was done with parts that were defective. So you aren't, just getting to continue it flat. You have to keep in mind that that's introduced. So we can't just solve problems by doing maintenance as early as possible, at extremely short intervals. Let's say even if it was for free, we could get better performance by truly measuring when the degradation is going to become a problem and taking as much time as possible, because that will be the least amount of cumulative opportunity for quality defects to occur. So in the case, with the bike, we have to decide what are the items that are the true, wear out mechanisms. And it could be something like the engine, right? Or it could be the frame. And this depends greatly on the products and what the higher level business model is. I mean, we all know that you can rebuild an engine, or you could swap out a frame, or you could keep welding it if there was, small cracks in it. But at some point, the cost model doesn't work. And that's part of, that original business plan for the product. And it changes over time as technology changes. We used to have, vacuum repair shops and television repair shops. And we would, these items that would wear out, we would keep them going. Whereas now, you don't see that anymore. And part of it is that we've greatly improved the reliability of these products, but also technology moves so fast that customers generally want to replace their product because they want new technology, right? You're almost disappointed that your old TV hasn't broken to some degree because all your neighbors have the cool new one with all the new features. So it can change. So that's why it's part of when you design the product, the market it's going into, and your objectives. You want to have the wear out be the right wear out, time to wear out, not too long, not too short, because it does come at a cost. And this is why accessory life testing is so critical to validate that you are hitting that target and allowing you to balance it by either making it last longer if needed or allow it to last, have a shorter life, which provides benefit for either cost point or, technology development. So are there any more questions on that? That was what I wanted to share about it. That's what you'll find in the book, and of course, much more. But, you'll find that these concepts are really quite simple. And, I think that you'll really enjoy it. And hopefully you can just read it on an airplane flight. But I'd love to take some more questions right now if there are any. Do either of the Dans have questions?
I got a lot of questions, Adam, but I just wanted to say thanks for the work that you're doing. This is important stuff. It's things I live with my clients every day. And the more people that we can get involved in these discussions and kind of understand the tools that are out there and how to prevent problems for them in the future is always awesome. So I just appreciate your work in this area and look forward to, working with you and other people as well.
Oh, it's fantastic. Thank you so much, Dan. Yeah. Dan's work's amazing too, with with the labs that that you are working with and running, your expansions that you're doing. And actually, I mean, Dan, if you want to take a moment and share with us, a little bit about the work of Unify, that'd be great.
Yeah, sure. My name's Dan McGinnis, and I appreciate that, Adam. I'm the lab director here at Unified, and we're mostly known as a packaging company. And I've worked in the lab business my whole life on some very interesting experiments, which I'm sure we all have been a part of. So, with that being said, these guys gave me the opportunity to take a packaging lab and really build it into a full-up product test lab. And as part of that offering, we do a ton of reliability testing. And then that mirrors right into life coming out of being shipped in the packaging. So we've helped a lot of clients who have called us up and said, hey, we have damage in packaging. And then we find out that it actually has nothing to do with the packaging. It has to do with a lot of the product design. And there's some funny stories out there too that I could go on forever, but I think
you will someday, because I'm getting you on the podcast so we can just tell our stories. Yeah.
If you guys want to laugh, get on the podcast that Adam and I are going to do. And there'll be some funny stories about reliability on French fries and some other things that you'd never even consider. So
yeah, it'll be a good time.
Yeah, I'm going to stop there. But if anyone needs any help or has any questions, feel free to reach out to me anytime. So thanks,
awesome.
Adam. I appreciate it.
Yeah, no problem. That's great. Thank you. Does anybody else have a question quick?
Yeah, Adam, I think I don't have any questions because this was so clear, very relevant. I appreciate all this information. Great presentation. And we should touch base with each other in case you want to present at the Boston Reliability Chapter meeting.
Absolutely. Happy to.
Month. Okay.
Yeah, happy to.
Okay. Feel free to reach out to me and I'm sure we can set something up.
Okay, great. Good. All right. Well, thank you everybody for attending, and the book's available on Amazon, and I look forward to talking to you all again soon.